going to discuss how we can derive the potential and field for an electric dipole, and this is going to be a first order expansion. In another video we'll talk a little bit more about multipole expansions. So just recall that a dipole is a pair of charges. We're going to put them here and here, plus q and minus q. That's the simplest definition of a dipole. You can define the dipole moment for a charge density, and I'll show you that in a moment. So if we had this pair of charges separated by a vector L, then the dipole moment in this simple dipole is just P is equal to Q times L. Please notice that's a small p, a lowercase p. And for a more general charge density, we would define, P is equal to the integral of R times rho, the charge density, dV over a volume. So that's for a general charge density. And we can, of course, expand the potential of a general charge density using a multipole approach, where we consider different moments of the charge distribution, so r squared, r cubed, etc. But let's just come back to the dipole potential itself, and let's just think about the geometry of the situation. So for the sake of simplicity, we're going to align the dipole along the z-axis. So here we have z, here we have x, here we have y in a standard right-handed set. We're going to put the two charges here and here. That's plus q and that's minus q again. And we're going to be observing at some point here r1. And I'll draw the vector to r1, and this angle here is theta. That's a relatively simple and straightforward thing. We can write down the vector from the plus charge and the minus charge. So the vector from the plus charge to r1 is r plus, and that's equal to r1 minus L. Let's actually write it slightly differently. Let's write that as a half L, whereas r minus is given by r1 plus a half L. You can understand that because in order to go from this plus charge to r1, we have to go minus L over 2 plus r1, whereas the other way you have to go plus L over 2 and r1. Now we could just write down the potential as that stands. So we could write, for instance, V at r1 is equal to Q over 4 pi epsilon naught into 1 over r plus minus 1 over r minus. And you can do that, and if you have a computer you can solve that. But we want to write something a little more helpful. We want to expand out purely in terms of r1 itself. We don't want these r pluses and r minuses sitting here. So we're going to consider the magnitude of r plus. So let's start with just the vector product, the dot product of r plus dotted with r plus. And just using the formula up above, that's going to give us r1 squared plus L squared over 4. Actually, just for consistency, let's rewrite that as a quarter L squared. And we're going to have minus a half R1 dotted with L minus a half L dotted with R1. Now, of course, dot product is commutative, so we can change that to R1 squared plus a quarter L squared minus R1 dotted with L. Now, what's R1 dotted with L? Well, if we go back up to our diagram, we can see that here's the vector L, here's R1, so the dot product is going to be a cos theta. It's going to bring in a cos theta. So overall, we can say that that's equal to R1 squared plus a quarter L squared minus R1 L cos theta. Now, we want to write in terms of R1 because that's the point that we control. It's the place where we're making the observation. So we'll pull a factor of R1 squared outside and write everything else in the form of 1 plus something. And then, of course, in the standard way that physicists do, we will expand. So we now have R1 squared into 1 plus a quarter L squared over R1 squared minus L over R1 cos theta. And notice that when I have a vector, I underline it. When I don't have a vector, when I have a magnitude, I don't. This may seem like a small and a trivial point, but it's actually extremely important for clarity. At this point, I just want to point out to you that we could think of P dotted with R1 hat that's going to be QL dotted with R1 hat, which is just going to be QL cos theta. That's a point that will come up later. You can see already why I've written that from the presence of this L cos theta here. Okay, so let's think about what we actually need to do. In order to calculate the potential, we need to find a 1 over R plus and a 1 over R minus. So let's write those out. So 1 over R plus is given by 1 over R1 into 1 plus a quarter L squared over R1 squared minus L over R1 cos theta to the factor of minus a half, which we can write as 1 over R1 into 1 plus L over R1 cos theta, sorry, L over 2R1, because that's a factor of a half. And then we would also, if we were being complete, add in a factor of minus 1 over 8 L squared over R1 squared. That's an approximate expansion, and this is using the binomial expansion, where we're writing 1 plus delta to the power n is approximately equal to 1 plus n delta, and we've made, oops, it's not a very good curly bracket, L squared, we've made this term here equal to delta. This is delta. We're going to discard terms which are second order or above, so L squared over R1 squared and above. For the sake of simplicity, actually we'll see that the second order terms in this case would cancel. So 1 over R minus, which you can do for yourself as an exercise, is 1 over R1 into 1 minus L over 2R1 cos theta minus 1/8 L squared over R1 squared. Okay, so now we can add those two together, or take the difference between them, because that's what we need. So we can say that 1 over R plus minus 1 over R minus is given by 1 over R1 into 1, sorry, not 1, I'm talking rubbish, let me just rephrase that, is equal to L over R1 squared cos theta. And what we see is that the factor of 1 cancels. If we were retaining them, these factors of L squared over R squared would cancel, and these two sum because we have the minus sign here, cancelled by the minus sign outside the 1 over R minus, and we get 2 of those factors. And that then gives us the potential. Therefore, V at R1 is equal to QL cos theta over 4 pi epsilon naught R1, which we can also write as P dotted with R1 hat over 4 pi epsilon naught R1 squared. And if you wanted to, sorry, there should be a squared here, you could write that as P dot R1 over 4 pi epsilon naught R1 cubed. This has the right dimension. It goes like it's QL over R1 squared. So dimensionally, we've got a factor of 1 over distance. However, when we vary R1, which is the thing we have control over, the potential will scale as 1 over R1 squared. So it'll fall off faster than you would get the potential from a monopole. We could write down the electric field. So E is just minus the gradient of V. And in spherical polar coordinates, it's fairly easy to show that ER is equal to 2 QL cos theta over 4 pi epsilon naught R cubed. And that's because E has taken a gradient, and E theta is QL sine theta over 4 pi epsilon naught R1 cubed. There should be a 1 on there. So the potential is always 0 along the centre line, where theta is pi over 2. The field decays as 1 over R1 cubed, and the potential decays as 1 over R1 squared. So this was a slightly a slow and slightly laboured explanation of how we do this expansion. It's good to know how to do it. Now what we can do, of course, is we can then put this into a computer simulation. And so let me just show you here what we have. So this is a Python notebook that's available on GitHub and also on the Moodle pages, where I've coded up the electric dipole. So you'll see here in this first cell, we set the size as being 10 in each direction. That's an arbitrary size, and actually what we're going to do is we're going to zoom in and out on the dipole by changing the length of the dipole. You can see that where it's defining the variable dipole L. At the moment that's defined as 1, so that's a small fraction of the total size of the simulation area. We start off by defining x and z, and then we calculate r and theta from that, and I've plotted some contour values. Now here we see how you calculate the exact dipole. So we put the dipole centered on the origin, and then this array Rp and Rm are arrays of the points R plus and R minus, and down at the bottom of cell 3 here, we just find the total exact potential just by adding them up. And we can plot that, and here's an example of the plot. You can see it's the standard dipole where you've got a positive potential near the top and a negative potential near the bottom where the plus and minus charges are. We can, of course, then calculate the approximate potential using QL cos theta over r squared. I've set 4 pi epsilon 0 to 1 just for simplicity. And when we do that, we see this form. To first inspection, the two look very similar. If you look quite carefully, then in between the charges, they differ somewhat. And if we plot the difference between them, you can see here that the main difference is between the two charges. So at this distance, it's a good approximation. The field, again, we can plot exactly just by using Q over 4 pi epsilon 0 r squared. And that's what I'm doing here. I'm calculating the x and the z components of the plus charge. That's field px and field pz, and then the minus charge. And plotting it like this. And you see that we get the standard dipole field, which is sort of a very rounded shape. It's also very familiar from bar magnets. The approximate field, which I've written in spherical polars and then I've transformed into Cartesian polars down here, again, it looks quite similar. Though if you look very carefully, what you'll see is that actually for the real field, the exact field, particularly near the charges here, the field lines are not kind of pinching in towards the charges, whereas down here, the field lines are just starting to pinch in. So let's go back up and redefine the size of the potential. And let's change that to 8. So that's quite a large fraction of the cell. And let's rerun this. Oh dear, okay, it restarted itself. Let's run from the beginning. So now let's rerun this and plot it. Right, we've zoomed right in. And this is the exact potential, and you can see that there's a significant gap between the contour lines here because we're closer, and I haven't plotted contour lines out to very low values. When we plot the approximate potential, you can see why I'm making this point. That's here. Right, this is why I'm making that point. You see here that the contour lines for the approximate potential are not centered on the charges. So if we look back up to the exact potential, the contour lines are centered on the charges. And if we look down here, the charges are way out. This is a much worse approximation. It's not surprising because the potential that we calculated was for a perfect dipole with no length, or a very, very small length rather. And if we now plot the difference in potential, it's gone much further, and you can see that we've got all sorts of errors. The field, again, the exact field is the same, but we're just zoomed in, and now we see there's the classic dipole where you have the field lines going between the charges as well as everywhere else. But again, with the approximate field, we have a very, very small dipole here, and so you can see that you don't have that shape in between the two charges. You see here, you can see very clearly the effect of the approximation. It breaks down at this stage. This kind of numerical exploration of the approximate solution is actually very helpful for understanding and visualizing, and I would encourage you to do that and to look at the assumptions behind the dipole approximation. We'll look at a multipole expansion, which is where you can go to a full expansion to arbitrary accuracy in another video.